to went for a study in JICA University, Japan in 2022. I undertook a study that took me 2.5 years. I graduated this year in March with a master's degree in resource geology. This morning I am able to present my research findings, and the title of my research is Red Element Minerals and Geochemical Signature of Morobe, Granodiorite, Papua New Guinea. So while mentioning this, I want to acknowledge my academic supervisor, Professor Rio Takashi. He was really helpful during my study at JICA. So this will be the outline of my presentation for this morning. Please get it ready. Okay. The background. I was inspired to study rare elements because Papua New Guinea's national income relies heavily on mineral sales, which account for about 65% of our revenue. However, the global market for this commodity is highly volatile, posing risk to our economy. So to mitigate this risk, it's crucial to diversify our mineral resources. Like right now, we are looking more at gold and copper, but now we can see that there's a lot of fluctuation. So we need to diversify and go into critical minerals and rare elements. So that's what has inspired me to undertake the research into rare elements. So my research is basically to evaluate the potential rare deposits in PNG. So I decided to undertake a study on the Miocene intrusive rocks of Morobe Granodiorite. These slides illustrate the geology of the study area, which primarily consists of Cretaceous owens-daily metamorphics, which is marked by the green color on the map, and the Miocene Granodiorite intrusions, which is marked by the red color. So this is the black dots that you see are my sample distribution. I collected most of the samples from the granodiorites, and those circles, black anti-circle that you see is samples from Oside and Buckwheat 2023. Those are the sample distributions from the area that I studied. Okay, this slide shows work done by early researchers. The geological research and mineral exploration in the Morobe has started in 1920. I listed some of this research done by these researchers, and the table on the right-hand side summarizes the age dates mostly from Page and others, and the latest research that was done was by Oside and Buckwheat 2023. So my research is more like it complements on what they've been doing. So what are the research objectives? My research objectives is to evaluate geochemical patterns and determine the role of red-bearing minerals, and to identify the magmatic process responsible for the red distribution in the Morobe Granodiorite. So in order to achieve these objectives, I use the very listed here. I use petrography, X-ray diffraction, and scanning electron microscope microanalysis to identify mega and the accessory minerals present in the rocks and to determine the textile and mineral compositions. I also use EPMA to analyze the apatite chemistry. And for the bulk chemistry, I used XRF for analysis of major element concentration, and ICP-MS for the analysis of trace element concentration. So these are the analytical techniques that were carried out in JICA University for my project. Okay, those are the outcrop samples and end sample photos. These are representative samples that I've been using to. I was analyzing samples for my project. Okay, those rock samples, there were about 23 samples that I collected, and I had to classify these rocks into different classes. The samples were classified based on the model mineral count using the QAP diagram. So on the right hand side, you can see the names of rock samples that is classified to the according to the QAP diagram. So mostly they were monogranite and granodiorite, quartz monzonite diorite, monzodiorite, and quartz monzonite. Okay, this is one of the petrographic analysis that I did. One of the sample analyzed petrographically is quartz monzodiorite that represent early phase of intrusion. So this sample exhibits the cumulative texture with urethral to suburethral biotite, plagial clays, and amphiboles. So the trace of apatite, they occur as interstitial grains as well as inclusions within the plagial clays. So we can note from here that the abundance of apatite, hyphenite, and zircon in the samples were low. So actually, when I was doing the analysis, I didn't find the rare berry minerals like allanite and some of those common red bearings that usually carry the reds were absent. But I found most of them were apatite, titanite, and zircon. They were common. But in these rock samples, you didn't find most of these minerals, and I will have to explain why that happens later on. Okay, this slide shows quartz monzonite sample. It has plagiatic texture with suburethral crystal of amphibole, biotite and accessory minerals. So it can be noted here that this sample contains abundant apatite minerals. So we can also note the embayment texture in the plagial clays, which usually indicates melting. Okay, this is it's the late phase. This slide presents a sample of ablitic monzogranite, which represent the late phase intrusive. Within these sample, clusters of titanites were found along the contact between the granodiorite as shown in the picture. So titanite is the mineral that contains titanium. So it has an application in the it's a light metal that's used in aircraft and so I found abundance of this one in the applied lights. Okay, these slides present the nature and trace element variation diagrams along with the Conrad normalized spider diagrams. On the left-hand side of the slide, you will see elements associated with red bearing minerals, so negative correlations with respect to silica. This depletion trend suggests a fractionation of red bearing minerals. And on the right-hand side, Conrad normalized incompatible trace element, whether this shows the enrichment of large iron, liquefied elements, and depletion of high field strength elements. So it is these are the for the rare element patterns, granite and monodiorite indicate a strong rare depletion. So granite shows the prominent negative European minority. That's this one, and granite shows the prominent negative European minority, while monodiorite exhibits a prominent positive European anomaly. And additionally, one of the quartz monzonite sample shows elevated red elements. So the content of red elements in those different shoots of rocks were variable, but some of them were really depleted. So those are what we those are the rocks that needs to be investigated, why they are depleted and why are they enriched. So I will come to this later when I do the discussion. Okay, as I said, the common red bearing minerals were absent. But apatite was one of the major red bearing minerals that I found commonly occurring in most of the rocks that were studied. So I decided to do the chemical analysis for the apatite, look at its concentration. So this slide shows the bulk red composition of the rock type in the Morobe granodiorite. The quartz monodiorite shows the highest enrichment of red elements, followed by granodiorite, monogranite, and quartz monzonite. So the distribution of the light red elements and heavy red elements in each rock types mirrors that of the all the red elements. So basically, the earlier phases of intrusions, they have no rare content. The later phases of intrusions shows the depletion of the rare elements. So that's something that I will talk about a little bit later. This is The appetite mineral was mostly occurring as inclusions within the biotype, and there was some that occurs as the interstitial grains within the rock mass. Okay, I was using the ternary diagram of fluorine, and hydroxide to determine what type of appetite it was, and I found that most of it was it has high concentration of fluorine, so it is I classified it as fluoroappetite. Okay, I analyzed the concentration of red in the apatite. For the red concentration in the apatite, the latanium, cerium, and neodymium concentration increased from the rim to 4, while the concentration of yttrium remains stable across the rim. So the volatile concentration generally were consistent throughout the grains. So those were the composition of the red elements that I found in the apatite mineral. Okay, going into the discussion. So, in the chondrite normalized red element patterns, there were 4 distinct patterns displayed by different rock types. I will explain each of these. So here you can see there's quartz monzonite at the elevated amount of red elements, while granite, monzogranite, and quartz monzonite, they were strongly depleted from the red elements. So quartz monzonite shows a high concentration of the red elements and has intermediate to heavy composition. So this rock is likely formed before the apatite crystallization. So what I mean is there was enrichment in the red elements, and during the magmatic evolution, the red elements become enriched. It become enriched, and then when it reaches the saturation point, that's when the apatites start to crystallize out from the magma. So when it crystallized, it was using the red from the magma, so it started to deplete that. So you can see the trend is going down. So I've been using the phosphorus to use it as a proxy to show the crystallization of the apatite. Okay. The other sample showed high strontium to yttrium ratio of 219.4 and a prominent positive europium anomaly of 4, indicating a pressure-based accumulation. So this one, the increase For all the samples that I was analyzing, they show no European anomaly or negative European anomaly. But for this one, it showed strong positive European anomaly. So when I was looking at the petrography, I showed that placer plates were melting. So when the placer plates melts, they put the European plate into the network. So that's what increases the European anomaly. So and also for these samples, I found abundant apatite and checkpoint and magnetite that were that occurred as locations within the biotite as shown. Okay, the red element vector number 3 is mostly found in the intermediate rocks with typical magmatic arc granodiorite patterns. So these rocks show little to no European anomaly. Petrographic analysis revealed that they have apatite and zircon. They have more apatite and zircon in the the abundance of the apatite and zircon for these samples were higher than the magnetic rocks. But when we were looking at the concentration of the red elements in the intermediate rocks, they were lower. It's because they were the apatite were crystallizing and they were taking the reds out from the magma. So that's why the concentration was lower, but there was abundant minerals we saw in these intermediate rocks. For the last red patterns, that was the granitic samples. In the granitic samples, the red concentration was very low. It was very low because we had hornblende and apatite polyester was crystallizing. They were removing craters from the well, so they couldn't get the chance to go into the granitic